thank y'all for joining us today. And my name is Claire Swinford. I'm the director for the NASA Regional Educator Resource Center. And Patty Forehand, although it says Darlene McClendon, she's waving. That's our CEO's name on this Zoom account, so we couldn't fix that. But we do welcome you, and especially Justin as well. Patty works with me in the Resource Center as our professional development specialist and STEM instructor, so we're really pleased to be here today. Justin, I'm going to let him tell a little bit about himself, but we're thrilled to have him join us today. I think y'all are really going to enjoy his presentation. And so I'm going to turn it over to Justin and let him get started. And one more thing, though. We do have a PowerPoint that tells all about the Resource Center and the Museum of Aviation and its programs, which we will share with you after this presentation is over. We'll make sure and share that with you so that you know all about us. Thank you. Justin, I'll turn it over to you.
Thank you so much. Thank you for organizing. Thank you for being in charge. And I'm honored to be here, and I'm very excited to talk to you guys. My name, obviously, is Justin Robinson. I'm a fourth-year graduate student in astrophysics at Georgia State University. I look at other galaxies. I look at how fast they rotate. I look at how massive they are. And I look at how massive their giant black holes are that live in the centers of all of those massive galaxies. And I'm also one of the graduate lead ambassadors for the Georgia Outreach Team for Space, or GOT Space, that's funded and sponsored by the Georgia Space Grant Consortium. And for the past, I guess, almost 2.5 years now, since the fall of 2018, we have been traveling around Metro Atlanta, and now in the virtual world, even further than that, visiting middle schools, high schools, and just bringing really cool, interactive, very engaging presentations and STEM demonstrations to classrooms that range anywhere from kindergarten all the way up to 12th grade. So today I wanted to share with you two of our most popular presentations that usually range in the middle school to high school level, and they're baseline so that they can be shifted towards whatever audience that we're in front of. And I've been told that there are multiple grade level teachers here, which is great, which gives me the opportunity to show you how these topics can be scaled depending on which grade level that we're talking to. These are meant to be very, very interactive. And so I think that the best way to show you what we do and how these can be implemented in the classroom and how they can be applicable to different topics that are covered in STEM classes is to have you participate with me. So if anybody is willing, anytime that I ask a question, which is going to be very often during these presentations, if you know the answer, go ahead and shout it out. If you don't, go ahead and shout out what you think is the answer so that maybe we can have a little fun. You can see how the students interact and how they're engaged with these presentations. And then you can kind of get an idea as to how it works if we were actually in person or if this was actually a presentation that we were doing in a classroom. So the first presentation that I will be doing today deals with, let me see if I can go ahead and press play here. Everything is still sharing. You guys can see my screen okay?
Mm-hmm. I see it.
Perfect. Okay, perfect.
Yeah, perfectly. Nice.
Perfect. Perfect. So this first presentation deals a lot with forces, motion, gravity, a lot of kinematics and graph interpretation. So this leans more towards the high school level, but again, it can be shifted down into middle school quite easily. And I'll try and do my best to show that to you now. But we're going to be, and based on the title of this, is learning science through the lens of astronomy. Get it, lens, because we look through telescopes. Anyway, it's taking the things that students learn in the classroom and actually putting it, like applying it to something. And in this case, applying it to some of the coolest nearby celestial objects that we have in the universe. So today I'll be telling you about how we look at galaxies and what we can tell from them, what we can measure, given some basic science, mathematics, and graph interpretation. So just to start off with, I have a quick question. What is this?
A prism.
It is a prism, exactly. And what is that prism doing?
Show us the rainbows, Roy G. Biv, help us see how light bends, all sorts of stuff.
Exactly. And I think if anybody's raising their hand, just go ahead and skip that step. Just unmute yourself and shout it out. But that's exactly right. White light, which is a combination of all of the colors of the spectrum, Roy G. Biv, hits the prism, and then each color exits the prism at a different angle. The reason why that happens is because each color has an associated energy with it. If this was middle school, I would kind of stop the explanation there. If this was high school, I would go into wavelengths and delve more into how the EM spectrum works. But just for now, I'll say that each color has an associated energy with it. And given all of those different energies hitting the prism, they will hit it with the different energy and then exit at a different angle. And so you get this really nice fan of colors as it exits the spectrum. And this is exactly how a rainbow works. Each little droplet of rain, which is why, well, you'll explain, or you'll see why you're never going to see a rainbow when it's completely sunny outside. You need it to be raining or recently raining in order to have a rainbow. The reason why that is because each little droplet of rain acts as a little tiny prism. And so light from the sun will hit those little tiny droplets. They'll disperse out the rainbow, and then you'll get this really, really nice, beautiful arc rainbow across the sky. I have another question. What is this?
Body heat.
Sorry?
Body heat.
Body heat, exactly. Yeah. And what kind of instrument will we need to see an image that looks like this?
Infrared.
Infrared, exactly. An infrared detector. Infrared goggles, anything like that, exactly. What about this?
X-ray.
X-rays.
Yep. And how about this?
Hulk.
The Hulk. What made the Hulk the Hulk? What did he get hit with?
Was it gamma rays or something like that?
Gamma rays. Gamma rays, exactly. And so all this to say that each one of those is a different energy of light. And all of those that I just showed you are energies of light that we can't detect with our eyes. Our eyes are excellent detectors of a very small range of energies that light, particles of light, which are called photons, can have. So it's shown here. That little tiny block in the center is what our eyes are sensitive to. And that is a very, very small fraction of the total amount of energies that light can have. And the reason, and in order to detect those things, we have to make instruments that are sensitive to those energies of light, X-rays, infrared detectors, gamma ray detectors, all of those. And the way that it works is that these energies are expressed in terms of waves. So each longer wavelengths are lower energy. So things that are in your car, like radio, or the microwaves that are coming out of your kitchen, those are all very low energy. The energies that our eyes can detect are actually pretty strong. They're pretty highly energetic. And then you go into the energies of light that can be harmful, like UV radiation. That's a higher energy than stuff that we can detect. Gamma rays, which are the most energetic, those are way, way stronger than the things that we can detect, with our eyes at least. And here's another question. These are normally based in Atlanta. If we were going somewhere else, I would have a different picture of a city. But I promise you this isn't a trick question. Can we see the sun if it's cloudy?
You won't be able to see the sun, but you'll feel the rays of I forgot what it's called. That's why they still encourage you to wear sunblock and all that, the SPFs.
Exactly.
UV
yeah,
rays.
The UV radiation, exactly. Yeah, you can still get sunburned even if it's cloudy, but you won't be able to see the sun. That's exactly right. Why? Why can't you see the sun if it's cloudy? What are the clouds doing to the light that we can see from the sun?
It blocks the light. It creates shade.
Blocks the light. Exactly. It blocks the light. And I want to ask why it blocks the light. And it actually, whoever was speaking, I can't see all the names on top of my screen right now. But you said you can still feel that heat from the sun, even though you can't see it. That heat that you feel is still photons. It's still light. So why can you feel that and not see it? It's because those two things, the feeling of heat and actually seeing it, are two different types of energies. What you feel is the UV radiation. What you're seeing, that energy of light is so, the energies are so high and the wavelengths are so short that they get absorbed or scattered by clouds very, very easily. The longer wavelengths, the UV stuff is short enough that it's powerful enough to punch through. The longer wavelengths, the lower energy photons, are long enough that they can pass through clouds really, really easily. And this is why Does it matter whether it's raining, cloudy, or sunny when you're listening to the radio in your car? Anybody?
No,
No,
radio
Yes.
waves come right
No.
through.
exactly. And this is why. Radio is a very, very, very low energy of light, which means that it doesn't get affected as much by things like clouds or stuff in the way as optical light does. The photon, the energies that we can see with our eyes. Not even these very, very powerful research telescopes that professional scientists use can see light that's being blocked by clouds. These things, these two telescopes, one is in New Mexico, the Apache Point Observatory, and the other is actually the observatory that Georgia State University runs. Not even those, which are much, much, much more powerful detectors, can see through clouds if it's cloudy, because they are limited by the same limitations that our eyes are, because they're looking at the same energies of light. Because these things are designed to detect the same energies that we are, they just use really, really big mirrors as like a big light bucket. And so all the light comes in, they bounce off of the mirror, and they all get shot into one little detector. But they're the same limitations. If they're designed to see the same energies that we see, they're limited by the same things that we are. So in order to see, quote unquote, see stuff that's lower energies like microwaves, like radio, the stuff that your car antenna can detect, we need a completely different type of light bucket, of telescope. And so the thing that we need to use for something like that is something that looks like this. This is the Green Bank telescope in West Virginia. Now, just for give you size reference there, those are some trees in front of it, but this thing is as big as a football field. Now, there are a couple of different things here. My main question is, what is the main difference between this telescope and these telescopes? What is the main difference between the two?
Wavelength of the light they detect?
Yes, that is 100% true. What is the main difference in the design of the two? What do these have that this one does not have?
They have more as glass lenses, while
Yes.
that picks up kind of more wavelengths using a kind of antenna dish to.
Yes. Absolutely, absolutely. The other ones use mirrors. This one has no mirrors. Mirrors are extremely, extremely good reflectors of light that we can see, right? They're not good at reflecting other energies of light. And that's kind of one of the first mind-blowing things that I like to say is that when you look in a mirror, or when you look at any sort of reflection of yourself, you are not seeing a reflection of yourself. You're seeing a reflection of a reflection, right? In order for you to see something, your eye has to detect a photon. And so if you're looking in a mirror, any light source coming from my ceiling, I have a lamp right here, there's light coming from my computer. The reason why you see me is that light bounces off of me and then goes into my camera, or if we were in person, they would go into your eyes. So everything that you see is a reflection, which means when you're looking in a mirror, you're seeing a reflection of a reflection. The light will bounce off of me, it'll hit the mirror, and then it'll bounce into my eyes. So mirrors are very good at doing that with the energies that our eyes are sensitive to. But if we look at a different energy, a different kind of photon, we need a completely new beast. This thing is just a giant dish made up of very, very thick, dense material, which means that the lower energies that you have, meaning the longer the wavelengths are, you need a longer thing to reflect it. Mirrors are very thin because the wavelengths of the energies that we can detect with our eyes are very thin. Moving down the line, you need thicker and thicker, sturdier materials in order to reflect that light. So everything, all of those radio photons will hit this dish and then bounce up into that detector that's floating on top of it. That's kind of like the eyeball of the telescope. So my question is, how do we actually detect it? What does the radio telescope see? And how do all these things work? So let's say that I have my radio telescope here, and I have what's called a spectrum down here, which means that I collect all of the photons that I'm getting from whatever I'm looking at, and then I'm going to divide them up into their individual energies, into their individual wavelengths, and that's on the x-axis. And then all I'm going to ask is, how many photons am I counting at each wavelength or at each energy. And that's what's on the y-axis. So how many photons am I counting at every energy that my telescope can see? And like separating everything out into colors, basically. So let's say I had a cloud sitting in front of my telescope, and let's say that it was made of hydrogen atoms, hydrogen gas cloud right in front of my telescope. If you look at hydrogen with a radio telescope, what it sees is a lot of photons coming at one specific wavelength. So in my spectrum here, the only thing that these atoms, this cloud, if you were able to look at it in the radio, would be giving you is basically one color, one wavelength. And you would count a lot of photons at that one specific wavelength. Now, let's try and mess with this a little and see what happens. If I give this cloud a kick away from me, what is going to happen to the photons that I'm looking at, that I'm detecting, if I make something move away from me? Do you think something would change? Does anybody have an idea? What would happen to that line, what we call an emission line? Those things were emitted and I detected them as one line in my spectrum. Would anything happen to that emission line if I started to move the cloud away from me?
I think it probably will.
Okay.
I think
Can I give you a hint? What does a car sound like when you're standing and you hear it come towards you and away from you?
Well, the pitch changes.
The pitch changes, exactly. Can somebody, if somebody is willing, I always like to ask this, if somebody's willing, can somebody do the noise of a car going towards you? Exactly. Okay, what's happening there? Why is the pitch changing? The thing that's emitting sound, the engine, isn't changing at all. It's emitting sound just like it was and always will be, no matter how fast you're going. What's happening is that you are stationary and listening to something coming towards you. What happens there is that these sound waves that are coming out of this engine, if something is moving towards you, those sound waves get compressed. And so you hear more sound waves per second in your ear, which means that the pitch goes up. It's like everything gets compressed. You hear things at a higher frequency. The opposite effect happens when something is moving away from you. Those wavelengths are now getting stretched out. You hear less of that sound per second. So that to you sounds like the pitch of the engine has gone down, even though the engine has changed nothing about the sound that it's been emitting this whole time. That phenomenon exists in the exact same way with light, right? Because light can be represented as waves. And so if I push something away from me, that means that the wavelengths get stretched out. And so this emission line, whatever that I'm seeing, whatever color that I'm looking at, is going to be shifted down towards lower energies, right? It's kind of like I'm seeing less color per second, kind of that same kind of that analogy with sound. Whatever I'm seeing would be shifted towards longer wavelengths. And so let's take that idea, instead point my telescope into space. And instead of just looking at a cloud, I want to look at a galaxy, a whole galaxy, put a galaxy in my eyeball of my telescope. And I want to know what happens to this emission line. There's a couple of different things that we need to set up, but I want to put that in your mind. This shape is a very, very interesting phenomenon. And we're going to use this emission line from a real galaxy to make a real astronomical measurement here at the end of this talk. So the first thing that I need to know is, what do galaxies look like in the radio? If our eyes were sensitive instead to radio photons, what would we see? Here is an image of a nearby spiral galaxy, just like our Milky Way. Our Milky Way is a spiral galaxy. This is what it would look like to our eyes. If we went out into space and we were floating, we were looking at it, this is what the galaxy would look like to our eyes. For the same galaxy on the same scale, here's what the galaxy looks like in the ultraviolet. What are the differences between this image, the optical one, and the one on the bottom left corner, the ultraviolet one?
Well, I think this is probably the most obvious one out of all that probably are there. But I believe that the main difference is that we see a different color based on what our eyes see instead of what the ultraviolet sees. Because when you're looking at it with your bare eye, as the first picture, is it looks more green, while the other is a bit more purple. I also have noticed that it's a bit more thinner, the second one than the first one.
Yes, yes, exactly. Yeah, fantastic. So I would say ignore the color because ultraviolet is outside of the things that we can detect, which means it doesn't technically have a color. This thing is just
It has a
where
color. We just don't know what it is. We don't know what
Sorry?
the wavelength color is.
Yeah, but you got it there right at the end, is that it seems different. It seems thinner, right? Not only does it seem thinner, excuse me, can you guys see my cursor?
Yes.
What can you see in the details, like right outside here? So here we don't really see anything outside of this little green hue. Whoops. What's the difference between the things that pop up here and the things that we don't see here?
Well, you can see more detail of the spiral arms, I've noticed.
Exactly. You can see the spiral arms. Exactly. That means that between these two things, the top left one is the energies of light that we can see. The bottom left one is ultraviolet, which is a higher energy than the stuff that we can detect with our eyes. So if you're seeing completely different things in an energy that's higher than we can detect, that must mean that whatever we're seeing here is more energetic, which means that it's hotter. The temperature is hotter. So here, if you're tracing out the spiral arms, the reason for that is because in spiral arms are the places where galaxies make stars. And most of the time, if you have a lot of gas, which is the stuff that you need to make stars, our sun was created by a huge ball of gas right when it was being born. Those regions will be very, very, very hot because not only are you creating stars, but you have made stars, very, very big, bright blue stars that are much hotter than our sun. Those temperatures will emit in things that are more highly energetic than the stuff with our eyes. And so most of the places where you're making stars will shine really, really brightly, not in the optical, which is what we can see, but instead in the ultraviolet, which is a step higher in energy than the stuff that we can see. Okay, keeping that in mind, for the same galaxy on the same scale, finally, this is what it looks like in the radio. Now, what is the main difference between the optical, the ultraviolet, and now the radio?
The WSRT-HI actually shows more details of everything, the spirals, the stars. It also looks like it shows like our body temperatures and all that stuff.
Yep. And it's just bigger, right? It's like 3 times as big as the stuff that we would see with our eyes. And so this is one of the main things why we need to build all these different instruments in order to see the different energies of light. Because if we never built any of that stuff, if the only things that we observed in everyday life or in the universe with only our eyes, look how limited we are, right? If we only saw stuff with our eyes, we'd be cutting ourselves off from all the other details and information that we get from ultraviolet, from radio. I could show this thing in all of the different regions of energies that light can emit in. So we would be fundamentally limiting ourselves if we only saw stuff with our eyes. For galaxies, though, the one that shows the most detail and the most size of it, right? The galaxy looks biggest in the radio one, the one on the right. And so if I wanted to study a galaxy and see what it was doing and see the most that I could possibly look at, I'd probably want to look at the one in the radio, right? It just shows so much more. So let's keep that in mind. I'm going to put that in my telescope. And the other thing that we need to establish is that galaxies are moving. Everything in the universe is moving, right? You are standing on the surface of the Earth that's rotating around once a day, that's moving around the sun once a year, right? So galaxies, just like everything else, are rotating. So from our perspective, if the galaxy was rotating like this, somebody raise their hand.
Yes, I did.
What's up?
I didn't. Sorry to interrupt as well with my question, but
No worries.
I did realize on the slide before this that when you get closer up, it looks like it's more of a vortex. I've noticed as well. And
Yep,
after
that's
quickly
right.
reading these few sentences, it seems even more like a vortex. So I'm wondering, is that literally what a galaxy is? A type of
Somewhat.
vortex?
Yeah, somewhat. When you think of a vortex, you think of like a really, really fast spinning kind of tornado sort of thing.
Kind of.
Galaxies are huge. They're gigantic, right? Our galaxy is 30,000 light years in diameter, which means one photon would take 30,000 years to go from one side to the other, traveling at the speed of light. They're huge. And so even though those galaxies are rotating really fast, the actual behavior of the thing is very, very calm. So even though it looks like a vortex because it has that motion of spinning around, it's not going at like a super fast, crazy speed. Because think about it, we are in a spiral arm of the Milky Way galaxy. We're traveling at crazy speeds right now, but we don't really feel it because it's not a very violent process. We're just calmly rotating around with our galaxy. But that shape, though, you're completely correct. It looks like a vortex because this thing is spinning around and it's dragging all of that gas and all of those stars with it around.
Well, that's kind of my description of a vortex, but at the same time, it kind of isn't. Because here's what I'm thinking. So when I think of a vortex, I think of whirlpools or ocean current as a sort.
Right.
They can be the same if we're comparing those who I just mentioned. A whirlpool is a bit more violent and such, but at the same time, water currents are a bit more smooth ride as well,
Okay.
but also can be violent. When I say a vortex, I'm not considering a fast moving just circuit. I think of something that looks like a circle that is always spinning outwards. It doesn't have to be like a whirlpool always spinning around at high speeds. It can be any speed. But my thinking of a vortex is something that spins around, sending but keeping its shape together.
Well, if that's what you're thinking, then that is a perfect description of what galaxies do and what they look like.
Okay, thank you.
Awesome. So if we're looking at this space vortex or a galaxy, from our perspective, if something is rotating, in this case, it's rotating so that it's like one side is coming out of the screen, one side is going into the screen. From our perspective, one side is always coming at us and one side is always going away from us. And so back to that interpretation of the car coming towards you and going away from you, the part of the galaxy that's coming towards you, that light from the galaxy is going to be compressed a little bit, which means that it's going to shift to higher energies. For the light that we can see, a higher energy color, green is right in the middle of Roy G. Biv, a higher energy color would be going towards the blue side of the spectrum. Blue is a higher energy than red. Blue is hotter than red, which means that all of your household appliances are wrong physically. Red is not hot, blue is not cold, it's flipped. So the side that's coming towards you would be shifted more towards the higher energies. And the other part of the galaxy that's moving away from you, that'll be shifted towards lower energies or red. And because of the red and blue sides of the spectrum that we can see, we call that phenomenon redshift and blue shift. The stuff that's coming towards you is blue shifted. The stuff that's going away from you is red shifted. So whatever our radio telescope sees, if it's looking at a galaxy, that means that one emission line that we got from that gas cloud earlier, part of it will be shifted towards higher energies, and one part will be shifted towards lower energies. And now here's the part where you're going to help me make a real astronomical measurement. This is what a real radio telescope saw from looking at a real galaxy. I know because I'm the one who observed it 2 years ago. This is from a very nearby galaxy in the universe with a really supermassive black hole at its center. Before we make a measurement, does this shape remind anybody of anything? Yes, go ahead.
It does remind me of a few different things.
Mhm.
Like these little model business charts with going up and down, but it also
Oh, yeah.
looks like radio wave frequencies.
Yeah, huh? Hmm.
That's the main thing it looks like to me.
Sure. Let's think of something like non-scientific. Does just the bare shape of this remind anybody of anything?
Batman.
Batman, exactly. This is what I have lovingly referred to as the Batman signal. This is what this is what galaxies look like if your eyeballs were trained to look at this stuff in radio. So using this, if this wasn't rotating, we would have one single line, just like we did with the cloud. Because it's rotating, things are pushed to either side to lower and higher energies, which means that we can use this thing to measure how fast this galaxy is rotating. And here's the way that we do that. We take a look at the left ear here, and we see what speed it's moving at. So this looks like it's about 6,000 kilometers per second, right? And then we go and look at the right ear, and we see what speed is that. Can anybody tell me what's about? It doesn't have to be exact. What speed is the right ear moving at right here? Sitting about this tick mark here.
About
63.
63. Yep. So we've got 6,000 on one side and 63,000 on the other side. And so the way that we see how fast it's rotating is that we just subtract those two numbers. So what are we left with? We have 6,300 and 6,000. I'm pretending I'm in front of students, and so I know you guys can do the math. It means it's rotating at about 300 kilometers per second. Now, does anybody know the conversion from kilometers per second to miles per hour off the top of their head? I don't. Usually I would have kids sometimes they have computers in front of them, so I would go and have them look it up, just Google it, or go on their phones if the teacher allows. But the conversion says that if this thing is rotating at 300 kilometers per second, that means it's rotating at almost 700,000 miles per hour.
Jeez.
And this galaxy is actually very similar. One sec, I'll get to your question in just a sec. This galaxy is actually very similar to our Milky Way. And most galaxies like our Milky Way are rotating at about this speed. So here's what I want you to take away is that you are standing on the surface of the Earth or sitting or whatever. You're not moving, but the Earth is rotating on its axis once a day. The Earth is rocketing around the sun once a year. And our sun is moving around and pulling all of the objects of the solar system with it around the Milky Way at about 700,000 miles per hour.
Wow.
So you are rocketing through space at roughly 700,000 miles per hour right now. And that's the second mind-boggling thing that I had from this one. So somebody had a question. Go ahead.
Sorry. So it's kind of about how you were measuring that with wavelengths, or
Sure.
So I have two questions for examples, kind of. Pretty much as we were talking about vortexes and whirlpools, this just came into my head. If you used whatever you used to measure this, could you do the same with moving objects like a whirlpool or tornadoes or stuff like that?
Absolutely. Absolutely. It just depends on what things are they emitting and what instrument do I need to see the light that it's emitting. That's all.
That's actually how they determine if a tornado is about to be created, isn't it? They'll see a shift in the wind coming and going, and they say, okay, it's concentrated. It looked like they could find a funnel cloud.
Absolutely. Absolutely.
Yeah, I also remember doing something about tornadoes in one of my classes as well, about like how they get created, and possibly a little bit about how to tell when one's about to happen. But either way, my second kind of example question is, would it also work if you if you not only did this and pointed it at solar systems, but what about planets?
That is a fantastic question. Yes, this is how we know how fast each of the planets in the solar system is rotating. The same exact method. Because you have a ball, and that ball is rotating. With planets, they're not usually emitting as much in the radio as galaxies are. The galaxies are very, very gassy, and the gas is what emits in the radio. For planets, they reflect sunlight really, really easily. And so if we train our telescopes to see, like, detect that reflected sunlight, if the planet is rotating, that means that if a photon comes in and bounces off the surface of that planet, and that planet is moving towards you, it's going to kick that photon with a little bit more energy than it had. And the opposite effect happens. If a photon hits the part of the planet that's receding, it's going to lose some energy as it bounces away from you. And so you probably wouldn't see something that looks like Batman, but what you would see is something that's spread out a little bit, given the amount of energy that the photons got boosted from hitting the side of the planet that's moving towards you, or deboosted from the side of the planet that's moving away from you. And so you would have the same thing. You would just like measure the left and the right side, and that would give you how fast each planet is rotating. That's exactly how we've done it. Yeah, go ahead.
Sorry, I had my space bar locked onto the raise
No,
hand
it's fine.
button.
We're
But
good, we're
thank
good.
you for answering my kind of example questions. I think I'm starting to get what this kind of measurement would be looking like. So thank you.
Yeah, absolutely, absolutely. Are there any other questions about this? I want to make sure that I stay on time, so I want to bounce to the other presentation, but I'd be happy to take any other questions.
The only real quick thing I was with, the planets and the galaxies too, they're either moving towards us or away too. So there's going to be a slight correction for that. But if you're looking for rotation, then I guess that would cancel out because you're looking at that movement. If it's going away or it's coming, you're looking at it relative to each other anyway, right? So.
Right, that's actually perfect because we can get that also from this. The center of this thing will tell you how fast it's moving away from you. So we had 6,600, so that means that this galaxy is moving at about 6,150 kilometers per second away from us, which would also be the same if you observed any other planet, which they're not really moving away from us, they're moving, well, I guess there's some component of motion that's moving away, but you would be able to do that same kind of thing, where if something is moving towards you or away from you, something like this, where you put it through a spectrum, will tell you how fast it's moving towards you or away from you.
Cool.
Any other questions?
Not
Cool.
for me.
Well, let me switch to the other one that I have planned.
That Batman thing. For some reason, every time I saw that, it made me laugh. Especially that last part with an actual Batman costume.
Exactly.
Right.
That's one of my favorite things to show. Okay. Everybody can see my screen, right?
Absolutumundo.
Perfect. Okay.
Yeah.
So this presentation delves into the same kinds of topics. There is some basic physics here. This one focuses more on energy, density, the behavior of light with those specific amount of things, velocity. So this works good usually for middle school and high schools, but the physics will be toned down if it's towards a younger audience, because no matter what physics is involved, in my opinion, everybody should have at least a rudimentary understanding of this image. So first off, who here has seen this image or knows what this image is?
I have a pretty good guess.
Okay, all right. Well, so like people have seen this. Sometimes I've gone to audiences with kids who have never seen this before, which is a tragedy. But this is the first real image of a black hole that we have ever gotten. And if you ask me, and if you ask a lot of my colleagues, of the huge accomplishments in understanding the universe that humans have accomplished, which includes walking on the moon, discovering if there was water on Mars, Voyager leaving the solar system, this easily ranks up there. I don't know where it ranks, but if you ask me, all those things are just tied for first place. This is one of the greatest accomplishments that humanity has ever gotten, has ever been able to achieve. Because one of the things is, like, we never thought that we would be able to image a black hole to begin with. But also, the way that we did this, we turned half of the surface of the Earth into a telescope and had 300 people from 20 different countries working to produce this one gigantic leap forward in science. Now, if that doesn't inspire somebody to go into STEM, I have no ammunition left. I have no idea what else I could do to inspire. Like, if somebody was just thinking of STEM, knowing that that's a possibility and how collaborative it is, if people aren't at least inspired just by the thought of that, then I don't understand. But
Me neither. That is a beautiful thing to think about.
Yeah, I agree. Yeah, whatever, just horrible things have been going on in the past year, just have that thought in your mind, and that just makes me happy. But there's so much to unpack here, and because it's such a huge achievement, I want to see if I can get students, teachers, anybody that I show this talk to at least understand somewhat of what's going on here, because it's so important and because it's such a huge achievement. And luckily, that delves into stuff that the students are learning in STEM classes right now. So the first thing that I want to establish before we start understanding what's all going on here is, what is space-time? We are living in space-time. You move your hand, you just move your hand through space-time. The Earth is traveling through space-time as it rotates around the sun. Space-time is kind of like a fabric through which all the objects in the universe travel through. If you have mass, the stuff that you're made of, the things that make up the atoms in your body, if you have mass, you are creating a dent in the space-time fabric. The Earth creates a big enough dent in space-time so that the moon follows around its dent, and the sun makes a big enough dent in space-time to where all of the planets in the solar system and the outer bodies of the outer solar system, all of those really, really cold asteroids and comets, all of those are rotating and spiraling in the giant dent that the sun makes in space-time. Now, it's kind of hard to imagine that. Sometimes I'll have physical stuff that I'll bring with me, but the easiest way to see this is one of those big coin things that you toss a quarter in or a penny in and you watch it spiral down into the center. That's the same kind of thing. Whatever has a ton of mass, like the sun, for example, will be responsible for creating the dip in that thing that they built that all the quarters spiral around in. The only thing that's not quite the same is that this is kind of like a flat representation, right? You think of this and then you see that it's pointing down. Well, there is no down in space. Gravity doesn't point downwards, gravity points inwards. We are not feeling a force downwards, we're feeling a force towards the inside of the Earth, which means that we are stuck to the Earth just like the people in Australia are stuck to the Earth. Gravity doesn't point down, it points inward. So there is no falling down or spiraling down in the dents that are created by massive objects. It's in 3 dimensions. And so we're always kind of spiraling inwards without ever moving in a downward direction, if that makes sense. The other thing is that light follows the dents and the curves that are made by objects in space. If nothing was there, light would travel in straight lines, never running into anything, never like changing course or anything like that. What makes light travel more fun than that is that there's massive objects everywhere in space. And so whenever you create a curve or a dent, the light will also travel through that. It's just like us walking on the surface of the Earth. Sometimes we'll go up a mountain, sometimes we'll go into a canyon, all of that stuff. That's the exact same experience that light has as it travels through space-time. And we can actually see this happen. We can observe it. If we see a star that's close enough to the sun, that light that's coming from that star will be curved by the dent that the sun makes. And from us, once the photons hit us and we see, oh, where did that come from? And we see back into a straight line, and we'll see we've actually detected kind of like a double star situation where the star was too close to the sun, it got bent. And then when we try and trace that back, the star appears in a different place. And the change in the position of the star from what we see and where it actually is, that shows us how large, how powerful the dent that the sun in space actually made. And the farther you are from that dent, the less of the effect that happens until you get to the star in the bottom right corner, where it doesn't go into a curve or a dent that the sun made. It just travels right to us unperturbed. The more powerful version of this is when we look out into space and we see images that were taken by the Hubble Space Telescope, where it just kept its shutter open and collected as much light as it could from the faintest objects in the universe. And what we noticed is that when there's a collection of a lot of galaxies really close to each other, we call it a cluster of galaxies, the amount of mass that's concentrated in there is so huge that the dent that it makes in space is enormous. And so you see in the center here, these arcs of light that are kind of creating a little lens in front of that cluster of yellow galaxies. That's light that's coming from galaxies that are behind that cluster. And as the light from those galaxies travel and they hit that cluster, they are bent and what's called lensed. Like they are smeared around those galaxies by the time that they get to us. That is what we call gravitational lensing. And so whatever light that's unfortunate enough to be behind whatever is massive enough to create that big of a dent in space, they will crash into it and get lensed around that huge, massive object. And so keep that in mind. And now we're talking about massive objects that are bending things and creating huge dents in space. Nothing creates a bigger dent in space than a black hole. But I want to know why. How do I actually make a black hole? Well, the way that I would do that is by taking a massive object and start crushing it down. And the only thing that I want to track here is something called escape velocity, which is a jargony term that just means how fast do you need to travel to completely get away from something's gravity. The Earth, right? I can resist the Earth's gravitational pull for a second, but I'm pulled right back down because my legs can't generate enough energy for me to move at a fast enough speed to get away from it. I will always be pulled back down. I don't care how many times I do leg day in the gym, it's never going to happen. The escape velocity of Earth, the speed that rockets need to travel to get astronauts off of the surface of the Earth, is 20,000 miles per hour, I think, something like that, in the neighborhood of tens of thousands of miles per hour. That's how fast you need to get away from Earth. That's pretty fast. The Earth ain't that big comparatively. So if I had a ball of mass, whatever you want to make it, what I want to see is how does that velocity that I need to travel to get away from it change as I crush it down? What happens to the weight, the apparent weight of something as you crush a piece of paper? What happens? Does it get heavier or does it get lighter? Anybody?
It
I'd
gets
say
denser.
heavier.
Gets
What
heavier.
was the question again?
Gets more dense.
Sorry?
The mass
What was the
is
question? I missed the question. I'm
It
sorry.
gets more dense.
So if you crush a piece of paper, does it apparently to you get heavier or does it get lighter?
It just gets more dense, correct? The mass.
It gets more dense. Exactly. That's what I was trying to get at. Yes. So if this were older students, I would say density is mass over volume. And so if you decrease the volume, you're increasing the density. If not, I would just stick to kind of crushing things and seeing how it apparently, because if it feels more heavy to you, that just means that you've changed the density. And so that's the main thing here. If I change the size of this thing, that means that I'm making things denser. And I want to see what happens to the speed at which I would need to move away from this thing, given how I'm changing the density. And so the size of this arrow will tell me how the velocity is being affected. If the arrow grows, that means I would have to travel faster. So if these are high school students, I would try and remind them, if they're in intro physics, they better have learned vectors by now. And so the magnitude of the vector will change depending on how I'm changing the density. If not, I would just leave it as the arrow grows, which means you have to move faster. So if I crush it down just a little bit, it gets denser, which means that the gravity increases. So I would have to travel faster and faster to get away from it. Okay, well, let's keep doing that. Let's crush it down even more. Okay. What's the pattern here? What's happening to the escape velocity as I keep crushing this thing down?
The denser it is, the faster you have to go.
Exactly. And what's happening to the force of gravity then? If I have to keep moving faster to get away from it, what's happening to the gravity?
It's getting stronger.
Exactly. Okay. So let's just take a leap. Let's say I found some sort of mechanism that allowed me to crush this thing down basically infinitely. Then what would happen? Well, I would have to move infinitely fast. If I somehow crush this thing down to a point where I couldn't even look at it with a microscope, I have created something so dense that the speed at which I would need to move away from it is faster than anything I can imagine. Well, then what did I just create? I just created something that eventually would have a velocity you would need to go that actually is faster than the speed at which light rockets through the universe. If you do that, you have created something where photons themselves do not travel fast enough to get away from this thing. And so however much mass you started with before you started crushing it down, you have created now a region in space where the escape velocity, the speed at which you need to move away, is more than the speed of light. And then this boundary here separates you. If you move some sort of distance away from it, the farther you are away from something, the less the gravity is, right? What orbits faster, Mercury or Pluto? Anybody?
Mercury.
Mercury, exactly. Why does Mercury rotate faster than Pluto does?
It's closer to the sun, so the gravitational force is greater. Centrifugal.
Exactly. So if you're closer to something with mass, you feel more of the force of gravity. So the farther you move away from something, the smaller the escape velocity goes. And so you have created this region around that point that you crushed down where light isn't fast enough to escape. And we call that boundary of that region, we call that the event horizon, which is just a fancy way of saying that's the last place where photons have the power to escape and then can reach our eyes or whatever our detector is. If it's below that point, the photons will never escape. We will never detect them because they can't move fast enough to get to us. And so that's one of the misconceptions I think about black holes, is that they are not spheres. There is no surface. There is just a region in space that separates where photons can get away from this object that you've created and a place where they can't. And that region, that surface, is the thing that separates that boundary. And the distance from that thing that you crushed down with to begin with to that boundary in space, we call that the Schwarzschild radius, because the guy who calculated what that would be, his name was Carl Schwarzschild. It was a little after Albert Einstein when he first made his theory. So here's a non-trick question again. What would we see? If we created this in space, what would we see?
Nothing.
We wouldn't see a thing. Why? Because light can't escape, right? So this object wouldn't shine. We wouldn't see the object at all. So that begs the question, why even study black holes to begin with? Why is this image such a revolutionary thing if we can't even see the light that's coming from it? Well, it's exactly it. We don't see the light that's coming from it, but we can study the light that's around it from things that are orbiting it or things that are close to it that are shining brightly, that haven't fallen into the black hole yet. And so let's say that I had gas orbiting around the black hole. That stuff, if it's close enough, can actually tell us roughly where this object is. But this stuff has to be really, really hot. If you have stuff that's orbiting around a black hole, that gravity is so strong that it's making things orbit around really, really fast, which means that all of that stuff that the gas is made of is going to be causing friction like you've never seen. What happens when things, what happens with friction? If you rub your hands together, what happens? What do you feel?
Heat. Generate heat.
Okay. You generate heat. And then take it a step further. What happens when you generate heat? If you cause enough friction between rocks that if you're trying to start, well, I think I just gave it away, my bad. So once you cause friction, what does friction cause? And then,
Fire.
I'm sorry, what does heat cause? Fire, thank you. I didn't want to say it, I'm sorry.
Yeah,
It's like my third presentation today. Whew. Okay, so it causes heat, which causes fire, or in other words, light, photons. Friction causes heat, causes photons. And so this thing, whatever's around a black hole that hasn't fallen in yet, is going to shine so brightly because of how fast it's rotating and because how much friction is being caused by the stuff that's orbiting around it. When you have an object like that, or with anything in the universe, photons can only orbit in what's called stable orbits. For example, the moon has a stable orbit around the Earth, roughly, because its orbit doesn't really change. It's found something where it's balanced. It has fallen into like a very, very, what's the word I'm looking for? When the solar system was first forming, there was a lot of things roaming around, other things hitting each other, and so nothing was in a stable orbit because there was so much chaos going on. Now everything is much calmer. That's what I'm looking for. Everything has settled down into calm things that they can continuously do because they're not being influenced by anything else. So the moon has a stable orbit around the Earth because it rarely ever changes. The Earth has a stable orbit around the sun. It's been doing it for a couple of billion years, and it'll probably keep doing it for another couple of billion years. Photons are the exact same way. In order for us to see it, in order for us to see photons from something like this, it needs to be happening for a long amount of time. And so the only things that we can detect are things in stable orbits that have kept repeating themselves. So whatever photons that I have here in my little cartoon, these are orbiting in stable orbits, right? We haven't been here for a very long time. The amount of humans have been here relative to the age of the universe is minuscule. So in order for us to see anything in the universe, it has to have been happening for a long period of time in order for us randomly to pop up and see it. So these, let's say, are orbiting in stable orbits. They've been doing it for a really long time. Anything closer than that wouldn't be stable, which means that it got too close. Whatever speed that it's moving wasn't able to get away, and so it would spiral inwards. That's what we call an unstable orbit. We don't detect those things because they happen so fast. There's a very small chance that we would randomly look up and try and detect this thing, and then we would see that happen. We don't ever see that. There's a very small chance of us doing that. We see the stuff that's constantly doing the thing that it's been doing for a while. And so whatever stuff that's surrounding a black hole, it doesn't show you the outline of the black hole. It shows you the outline of the black hole and a little bit more space. Because you see this one, if we were able to see this one, it actually outlines where this black hole is. The photons that are in stable orbits are way out here. So they surround the black hole and a little bit of space out in front of it, because if they got into that space, they would lose their stable orbit and they would fall in. And getting back to the idea of mass makes dents in space and light has to follow those curves, how would it behave if light interacted with the dents that a black hole would cause? So let's say that this black hole had a disk of material around it, just like Saturn's rings, right? So I took that drawing that I had and then I just flipped it over like this, and so I tilted it. And so that disk is now kind of like edge on to our point of view. If I do that, the light that's coming from behind the black hole, from my point of view, some of it will get bent up around it, right? The light that's coming from behind the black hole, the stuff that's being lit up by the amount of friction, that stuff, as the photons emanated out of it, they would be bent up around the top and bent down below from the bottom. And so what we would actually see if we went out and looked at this is something that probably looks a little like this. Does this remind anybody of anything? Anybody see Interstellar? This is exactly why the black hole in Interstellar looks like that.
That was Gargantuan, I think, was the name of it, wasn't it?
Good.
Wasn't
Sorry,
that the name of the black hole? Gigantuan or Gigantuan?
Gargantua. Yeah. So this is exactly why the black hole in Interstellar, Gargantua, looks like this. There is a disk of things around it that are extremely hot and shining extremely brightly. The stuff behind the black hole, because the dent in space is so massive, things are bent up around it. And so that halo that we see, this right here, that's not a real physical structure. That's just the light that's being lensed around it. That stuff isn't real. If we went up and we soared over it, we would stop seeing that. Because if we were on top of it looking down, all of that light from the disk would just emanate up, and we would be able to detect it. There would be no bending anymore. Interstellar got a lot of things right. It missed one thing though, and this calls back to the other presentation that I was doing with the redshift and blue shift effect. Everything in the universe is moving, and 99% of objects, while they're moving, they're also rotating. So this stuff, let's say this disk is moving like this, rotating around the black hole in that direction. Just like the galaxy that we were looking at earlier, that means one side of the disk is always moving towards us, and one side of the disk is always moving away from us. You see these repeat ideas in astronomy always, because as soon as you learn these phenomena that happen everywhere, that's basically what astronomy is. Looking at the same effects in different places with different telescopes. That's what astronomy is. And so what would this look like then? The part of the disk that's coming towards us will get shifted to more energetic colors, which means the stuff that we can see, what's more energetic, blue or red?
Blue.
Blue, exactly. And then the stuff that's moving away from us will be shifted towards red. So the effect that this would have on the disk would look something like this. So the stuff that's coming towards us will be shifted towards a higher energy color, and the stuff that's moving away from us will be shifted towards a lower energy color. Okay, I'm going to try and get through this as much as I can. I'm going a little over, I apologize for that. We have all the stuff set up. I think that we have all the information that we need to understand what's going on in that black hole image. And so where is this black hole image coming from? It's coming from this. This is a giant elliptical galaxy that's about 22 times, so it's like 60 million light years away from us. And it's got a gigantic jet that's almost pointed directly at Earth. What's happening there? Why is there a jet? This is a simulation that somebody made of what's going on in this system. So we have a black hole in the center. We have that really hot disk, shiny disk of material, and we have stuff that's falling into the black hole. So what happens in this really, really chaotic system is that some things are falling in, but they don't quite fall in. It's kind of like they slingshot around. You hear that in science movies all the time. They're like, oh, we'll do the slingshot maneuver. We'll go around the moon and we'll get slingshot and we'll move faster. That's exactly what's happening here. Things get too close to the black hole. They get slingshotted outwards into a jet that's coming towards us. And this is the stuff right here. This is kind of like the disk that I was doing with my cartoons, except this is what we would actually see. This stuff is what we can detect with the radio telescopes that we put on half of the surface of the Earth. This is that disk material. So just like before, this is the stuff that's moving in stable orbits. And so the black hole is somewhere in here, right? In this smaller kind of thing here. My question is, that disk was like this. The animation that I showed you had the disk like this, which is where we got that lensing effect, where we got that halo. So if something is like this, what this animation will show you is how the image that we see changes if instead I take the system like this and then I start moving it in 3D like this. And I want to see what happens to the image that we see. Here's what happens. Isn't that cool? So if the disk is edge on to you, where you're like, you take a piece of paper and then you fold it and look at it like this, where you can barely see it, that's when we get the halo effect. We would also see something that would strip down in the middle. If something is face on, if we're seeing it like we're looking down over it and we're seeing the whole thing, that halo effect doesn't happen. All we see is the disk, because now we're kind of like on top of the black hole looking down. And so that tells us, depending on what image that we get, that tells us what orientation the black hole and its disk are. If we see something that's stripped in the middle and the halo, that means that that disk is edge on to us. And if we don't see that, that means that we're looking at it face on, where we see all of the disk. We're not seeing something that strips through the middle. And so we're building up to it. We're making all of our keys here.
I'm pretty sure I can actually see the overall shape of the black hole, kind of, as well.
Yep, you can. In fact, this is a time series of a bunch of different images that we got from that black hole, from all the telescopes that we put on Earth. This is a time series of all the images that were put together, right? And then it fades into this. So putting everything together, what can we tell from this thing, right? So this is, it should fade out into, yeah. So this is what's happening in the system. Our telescopes, even though we spread it out across the surface of the Earth, we still don't have a big enough telescope to see that much detail. So it's that's why it's kind of blurry. But this is what's happening in the system, and this is how the disk has to be oriented, right? So putting everything together, here's the final image. What we know is that this stuff has to be moving in stable orbits, which means that here, this isn't the black hole. This is the black hole somewhere in here. Whoops. This is the black hole somewhere in here with that area outside of it where photons can't stay in stable orbits. And so if you ever heard, we got the image of the shadow of the black hole, the shadow of the black hole is what a lot of press releases uses. That's what they mean. We don't see the black hole from these photons. We see the black hole plus its quote unquote shadow, the place around it where photons can no longer travel in stable orbits. But also, do we see a slice in the middle or not? Do we see anything going across the middle of the black hole?
Not from my perspective.
Exactly. Okay, so what does the orientation of the disk have to be? In 3D space, how is the disk placed on the black hole? Anybody with their hand, try and show me. If we don't see the strip in the middle, where does the disk have to be oriented? Exactly, yeah. Angela got it, yeah, just like this, right? Which means that we're seeing it face on. There's nothing cutting through the center, and so this disk has to be facing towards us like this. The last thing though, why is the bottom brighter than the top? Maybe I should ask this question. Why is the bottom at a higher energy color than the top?
Is it moving towards us?
Yeah. So how, if the disk is like this, how is the bottom moving towards us and the top moving away from us? This is where in class, everybody's like trying to look at their hand and do this kind of thing. It means that if the disk is like this, if I had a piece of paper, this would work. If the disk was like this, completely, oh no, my background is white and that's why the virtual stuff. Anyway, if the disk was like this, completely face on, flat. In order for the bottom to be moving towards us, if the disk was rotating like this, let's see if I do this right. If it's rotating like this, that means that the disk would have to be pushed and angled just slightly towards us, where the bottom would get boosted a bit towards our direction, and the top would be deboosted a bit this direction. So it is just slightly angled towards us that way to get that orientation right, where the bottom gets boosted and the top gets deboosted. So just in this image alone, this single image, we can see how big that shadow of the black hole is, which actually means with our math, we can tell how big the black hole is physically, given how big that shadow is. We know the orientation of the disk. We have an idea of how fast it's rotating, because the brighter that bottom would be and the dimmer that top would be, in order for that to work, it would have to give more of a boost, which means it would have to be moving fast, or it would have to be moving faster. So the size of the shadow, the orientation of the disk, how fast it's rotating, all of that stuff to unpack in one single image that we got from this. And we're even doing more. In 2020, in September, a couple of months ago, they put together images from the different time periods where they were observing the disk. And it's changing. It's wobbling. You can see that the brightness is changing. It's switching from top to bottom. Now, if we just run through that analysis, we're saying that one side has to be tilted towards us in order for that to happen. What is causing this? Why would it flip? Why would the top be more brighter than the bottom?
Well, it's moving, so wouldn't that account for part of that?
Yep, that's exactly right. The whole thing is shifting like this. This thing, it's like it's kind of staying in the plane, just like this, like flat, but the chaosness of this whole thing is causing this disk to wobble and kind of do a little shimmy in space like this, where sometimes the part that's boosted, that's coming towards us, is the top, and sometimes the part that's boosted is the bottom over time, over years. which is insane. Things don't change on yearly timescales in astronomy. Things change on millions of years of timescales. So the fact that we are looking at something that's 60 million light years away and that's changing on timescales like this is absolutely incredible. So I've gone a little over time, but the next target of this is going to be our black hole in the center of our Milky Way. So we've already traced out the motion of stars in the center of our galaxy. It looks like this, that are all rotating around a supermassive black hole at the center. We call it Sagittarius A star. So the next image, and I just listened to a talk about this today, they're thinking by sometime this year, the next thing that this telescope is going to release is the image of our black hole at the center of our galaxy. Whew. I will be happy to take any questions.
Yeah, just
I'm sorry I went over time. I'm so sorry.
No, that is great. This has been so amazing. We do have some questions in the chat box and some people who would like to ask you some. So having a question and answer session would be wonderful. Thank you.
Sure. Yeah.
All right. I know Sophia had a question in the box, and I know Andrew also has a couple of questions. Is that correct?
Now I see. I see.
I was just trying to respond to them. I see all the questions. Do you want me to read them out real quick?
Sure. Yeah, that'd be great.
Okay. Just trying to find the first one. Okay. First one. How does space garbage affect space? For example, debris or broken satellite dishes, etc.
Gotcha. It has a huge effect. We're putting stuff into space that orbits around Earth, which means that anything that we send out into space, astronauts, rockets, satellites, rovers on other planets, things that are meant to travel outside of the solar system like Voyager. Not only do we have to calculate how to maneuver those things and how fast they need to travel and when to launch them and how to launch them, but we also now need to take into account, well, now we got to make sure that they don't run into anything that's orbiting around Earth that's a piece of garbage, right? Which means that we've now had to find ways to track the stuff that we've put up there. For us, and this goes into SpaceX too, when those I think it's called Starlink, whatever things that they're putting out in space that gives people Wi-Fi, that stuff and garbage reflects light. The SpaceX stuff especially reflects light, which means that at night when we're trying to see things and we're trying to observe things and make discoveries, now we got to worry about something that's super close to our telescope that's reflecting light, more powerful than the stuff that we're observing out in space is emitting light and getting to us. And so our observations sometimes are screwed because of some dust that's reflecting light or the Starlink stuff that's reflecting light. Anything that's in the way of the surface of the Earth and outer space is an issue for us. So let's stop doing that.
Okay, so there's only like one or two more questions. This next one is from the same person. Is that to say a black hole is very cold within its depth or very hot because of the friction? Also, is a black hole something like a space quicksand? If you get stuck in one, the gravitational pull will suck you into it infinitely?
That is two great questions. The first one is black hole hot or cold? A black hole is about the coldest thing in the universe. Because in order for something to have heat is just emitting photons at a different energy. If we were able to see all of us in infrared light, especially me, because it's very hot in my room right now, I would be emitting a lot of infrared radiation. That's how heat escapes your body, as photons. A black hole does not emit photons, which means that it cannot emit heat. There's very, very complicated physics that says why it's not absolute zero. But for all intents and purposes, a black hole is one of the coldest objects that the universe creates. The stuff around it, though, that's still able to emit light is extremely hot. Like millions, probably on the order of billions of degrees. whatever is the stuff that's very, very, very close that's rotating around it. The second question, if you fall in, is it like quicksand? Yes, once you fall in, yes. I like the analogy more that black holes are like quicksand instead of black holes are like vacuum cleaners, because black holes don't suck. That's one of my taglines that I love to use. Black holes are not vacuum cleaners. They are not gigantic, sucking vortexes. They are just gravity on steroids. If you replace the sun with a black hole that had the same mass as the sun, what would happen? Do you think that if I replace it with the same amount of mass, do you think that the planets would change what they're doing, or do you think everything would fall in? Anybody want to take a guess?
Sorry, I thought you were just waiting for the person to say something. I'd have to say they'd probably all fall in.
Okay, that's usually the guess, and I don't blame you for thinking that, but that's why I'm trying to get rid of all these misconceptions. Nothing would change. I have taken the sun and I've replaced it with an equal amount of mass. It doesn't matter what that mass is. It could be a black hole, it could be a neutron star, it could be a white dwarf. It doesn't matter. It's the same amount of mass, which means that the gravity that each of the planets feel doesn't change. It would get cold and dark, sure, but the orbits of the planets would no longer change. So I like black holes as quicksand instead of black holes like vacuum cleaners.
Well, yeah. Those were the only messages. I don't know if she wants to reply, so I'm just gonna mute myself.
Okay, are there any other questions?
You pretty much answered mine.
I think, Sarah, I think you're muted.
I'm going to have to say, Andrew, you did a really good job co-hosting. You're a natural at this, you really are. So, and
Great.
Justin, that was an amazing workshop.
Yes, there really was.
Thank you. And I guess it's a shameful advertisement for us, because you can reach out to us anytime and we'd be more than happy to bring these to your classrooms. And in the virtual world too, we can be virtually anywhere. So these are completely available upon request, and all of our materials are open to you as well. So hopefully this has sparked some ideas on how to connect whatever you're doing in the classroom to the stuff that we have. We have many more presentations than this. We have topics that span almost all of the astronomy topics that we can think of that can adapt to any classroom. And so if you reach out to us, normally we'll ask what the curriculum is and the grades, so that we are the grades of the classes that we'll visit, and so that we can skew everything towards and relate to as much as you're teaching as possible.
Justin, I just want to say thank you. That was amazing. I wish I understood completely everything, but it's fascinating anyway.
I agree. Thank you very much.
Yes.
But it really was great, and we certainly appreciate you being a part of this, and I know we'll have you back again. And I do want to make sure everyone does know that we will send out a recording to you of this session so that you will have that. We've also been posting those on our website, archiving all the workshops that we have done. And I'll make sure you have that information too, so you can go back and relook at some, or look at some that you haven't, weren't able to be a part of at that time. And Justin, if there's where you can share your PowerPoint, that type of thing with us, I'll make sure that that's included for the teachers to have as well. And
I see that Lori put the link to our website in the chat. Thank you so much, Lori.
Yep.
That has
that.
a form you submit to us, and we get that immediately, and we respond immediately. So, and it has all of the, all if not most of the topics that we cover on that website too. So.
right. And when I send that email out, I'll make sure I include that link as well, just so everybody's got it.
Thank you, Claire. I was going to say too that if you don't see a topic specifically that you're interested in having either Justin and or a different Got Space ambassador engage with your class with, just reach out to us and say, I have no idea what what I'm interested in, but here are some dates. And, you know, Justin is working with a teacher right now who's never had us present to his class before, but, you know, they're putting together some things with basically that much knowledge and information. And we know the grade, we know the time and the day, and that's about it.
Which isn't a new scenario, to be honest. So we're used to that.
Also, Justin.
Yeah.
A couple things before we go. I really enjoyed the PowerPoint.
Thank you.
Well,
Thank you.
both of them actually. It was a really great PowerPoint, both of them. They described a lot and helped me learn a lot of new things about well, the main topics, black holes, red and blue shifts. It's a pretty cool thing.
Thank you.
Also,
Appreciate
second,
that.
if you ever want to I wasn't joking before when you asked about the help.
Right.
I seriously would not mind. So if you ever want me to help you with any class, I'd always be happy to do it.
Perfect. I appreciate that. Thank you so much. I will keep
And
that
just
in mind.
overall, thanks for sharing the PowerPoint and letting me come to the workshop.
Yeah, absolutely. Thank you. Thank you so much.
So we're glad you could join us today, Andrew.
Yeah,
It's inspiring.
that's wonderful.
So,
Honestly, this was actually just a random thing for me at first, because I honestly had no clue about this until my mom sent a Gmail. But I'm very glad she did.
Well, we are very glad that
Can you
you
do
joined
second
us.
grade?
6th.
Justin, can you do second grade things with stars and light? I have a gifted class, so they're a little bit above where the normal kids would be. But
Absolutely.
I think that would be fun for them to actually hear from someone who knows the astrophysics and not me just kind of winging it as we go.
Yes. We have presentations that are only made about stars and how stars work, and so that can be easily tweaked for a second grade classroom. Absolutely.
That would be awesome. Okay. So I will see what we can do about hooking it up, because they've been playing with the spectrum. They have a little bit of an understanding of troughs and that sort of thing, and the wavelengths, and they have a little bit, you know, they are 7 and 8, but I think it would be awesome to have them hear from someone who, as those questions pop in their head, they actually could get really good answers and not let me look that up.
Yeah. What's a shame is that when we do that, when we come to classrooms, we usually, for those kind of topics, we bring those diffraction glasses that look like 3D glasses with a rainbow thing in front of them. Yeah.
Yes. And they actually have done that, and they put the lasers through the spectral lenses and looked at where it read on the spectral lens, and we
they're doing that in second grade?
Yes, and we get in the closet and we play with the lasers and bounce the light around the closet and things like that because it's really dark. Yeah, they laugh at me every year when I take them in the closet. They're like, "Oh, she's taking them in the closet again." And we go in the closet and we get the lasers out and bounce them around and play with the red light and the blue and the green and different colors to see what they do.
That is absolutely incredible. I want to do that. Can I visit your class?
We actually burned chemicals this week so that they could see how fireworks were kind of like stars. And I actually had to get the fire marshal to approve, and he made me put a fire extinguisher in the room. He's like, "Nope, you're putting a fire extinguisher in there," because we burned like boric acid and a couple other things so they could see the different colors of the burning and start understanding that gases burn different colors and things like that.
Oh my God.
So, you know,
you're making my second grade sound so lame in comparison. This sounds absolutely incredible.
We try.
I'll tell you,
it'd be awesome.
I'll tell you, Justin, Dawn's been doing this for years with her students, and she is phenomenal. She has been coming to the NASA programs and workshops that we've done and help also present them for years. And she takes anything and everything back to those second graders. She'd be amazed even more what she does with them. So she's credit to her profession, as we all are, but
you never know when you're going to spark that one kid that says, "I want to be astrophysicist because we played in the closet with the laser." You never know. So
Hey, Justin,
Yeah.
I'm sorry to interrupt. Do you do anything? We have a planetarium at the museum, and it's got a nice package of stuff right there. But I was wondering, do you ever do anything, little presentations that maybe we could play inside the planetarium or something at the same time that we've got the stars and the planets up there? Have you ever done anything like that? I mean, I like your format. I like the way you do it.
Not at a planetarium, but I would jump at the opportunity to do anything like that.
Yeah. Well, we
don't have access to
yeah. Okay.
We've done stuff with telescopes. We've done stuff at the observatory where we'll have talks, and we'll have talks in the dome of the telescope, and I'll move it around with different objects, and like take exposures with the CCD and show them a couple of those things. But to do something in a planetarium would be amazing.
Yeah. Okay. All right.
We already sent out the link to our website, and I'll see the requests that come in. But in case you want to contact me directly, I just put my email in the chat. See if I spelled it right.
Okay. Thank you, Justin. And I was going to include that information in my email.
Cool.
I keep making a list.
you know, Claire, that was going to be my next question. Can you send it to me, because I'm on my phone and I don't want to download it all to the phone.
Right. I will send an email out with all this information and make sure that everyone has it. Yes.
Claire, thanks for that invite. I really like this.
You're welcome. You're welcome. Kim works with us at the Museum of Aviation, so he happened to be by today, and I know he likes space. And,
oh yeah.
And all
Well,
of
I'm headed on the aviation side right now, but I'm always kind of bugging Claire, so I'm always in her office, asking if she needs help or anything like that. So
right. Yeah, well, I'm glad he's on. Thank you to everybody who came and who listened. And thank you to those. I see everybody's videos now, which is great. But an extra special thank you to those who had their videos on. Which it's nice to see faces when I'm doing these things. It makes it almost feel normal. So I really appreciate that from my point of view. So thank you very much, and thank you everybody for listening and for your questions and for volunteering. This was so much fun.
Well, thank you for sharing this with us.
Yeah, absolutely.
Yes. Well, everyone have a great rest of the week. A very happy new year. And if there's anything else that Patty and I can do to help anyone, please let us know. We're there to help provide these types of services and resources. And if we can't find it, we'll find someone who knows where it is, and we'll get it to you. So
That's right.
quite resourceful. So, but anyway, thank you again, Justin, and Lori. Thank you for being with us today too. And Space Grant is just awesome. They have such great programs and help support great programs. So we appreciate it, and hope to see you out in the schools a little bit more.
Us too.
All right. Thank you again. And we will see y'all in the future.
All right. Bye, everyone.
Well, bye, everyone.
Bye,
And
everyone.
thanks for letting me join you all.
You're welcome. Thank you for joining us. Bye.
Yeah, thank you for joining us, Andrew. Great having you.
Thanks.
Bye-bye.
Bye, everybody.